Hello everyone, welcome back to David IB course. Today, we're journeying into the strangest, most mind-bending world ever discovered by science, the world of quantum physics. This isn't just another science lesson. This is a trip down the rabbit hole, to a place where the very act of looking at something changes what you see. It's a realm that challenges our most fundamental understanding of reality itself. For centuries, we were comfortable with what we call classical physics. It's the physics of our everyday lives. It's a predictable world where apples fall from trees and planets orbit the sun in neat, calculable paths. It's the physics of Isaac Newton, a world of solid objects with definite properties and locations. It's logical, it's intuitive, and it built the modern world. But about 100 years ago, scientists started poking around at the very, very small, the world inside the atom. And what they found there shattered everything. They discovered that the rules governing the universe at its most fundamental level are nothing like the rules we experience day to day. This new set of rules is what we call quantum mechanics. And here's the most incredible part. While classical physics explains big things, quantum physics explains everything, including the big things. It's the ultimate operating system of the universe. So what are these bizarre new rules? Let's start with the first shock: wave-particle duality. In our world, things are either particles, like a grain of sand, or they are waves, like a ripple in a pond. They are distinct categories, but in the quantum world, this distinction collapses. Tiny things like electrons, which we always thought of as microscopic little balls, can also behave like spread-out waves. It's not that they are sometimes a particle and sometimes a wave. They are somehow both, all at once. Imagine a coin that is both heads and tails simultaneously until the moment it lands. This isn't a metaphor. It's the verified reality for the building blocks of our universe. To see this in action, let's look at one of the most famous experiments in all of physics, the double slit experiment. It's simple in its setup, but profound in its implications. Scientists set up a barrier with two narrow slits in it and decided to fire electrons, one by one, towards it. Behind the barrier was a detector screen to see where they landed. Now, if electrons are just tiny particles like little bullets, you'd expect to see two distinct bands on the screen right behind each slit. Simple, but that's not what they saw. Instead, they saw a pattern of many bands, an interference pattern, which is the classic signature of waves. When waves pass through the slits, they interfere with each other, creating peaks and troughs, just like water waves. This meant that each single electron traveling alone was somehow passing through both slits at the same time, as a wave, and interfering with itself. This is utterly bizarre. Can one thing be in two places at once? But here's where it gets truly mind-blowing. The physicists, baffled by this result, decided to get sneaky. They placed a tiny detector right at the slits to find out which one each electron actually went through. They wanted to catch the electron in the act. The moment they did that, the moment they observed the electrons to see their path, the whole pattern changed. The interference pattern vanished completely. Now what appeared on the screen? Two simple bands. Exactly what you would expect from particles. The very act of measuring, of observing which slit the electron went through, forced it to choose a path and behave like a particle. The wave behavior disappeared. Let that sink in. The reality of the electron's state, whether it acts as a wave or a particle, depended on whether or not someone was watching. This suggests that at the quantum level, reality itself is flexible and seems to respond to observation. This observation problem led to one of the most famous thought experiments ever conceived. Proposed by the Austrian physicist Erwin Schrödinger in 1935, it's called Schrödinger's cat. Imagine a cat is placed inside a sealed box. Along with the cat, there is a tiny amount of radioactive material. The atoms in this material are governed by quantum mechanics, so they exist in a state of superposition, both decayed and not decayed at the same time. This is connected to a Geiger counter, which, if it detects decay, will trigger a hammer to smash a vial of poison, which would then kill the cat, according to the strange rules of quantum physics, until someone opens the box and observes the system. The radioactive atom is in a superposition of both decayed and not decayed. Therefore, the Geiger counter is both triggered and not triggered. The poison is both released and not released, and the cat. Well, the cat is both alive and dead at the same time. Exists in a blurry, probabilistic state of all possibilities at once. It's only when you open the box and make an observation that reality is forced to collapse into one definite state. Either the cat is alive, or it's dead. This thought experiment brilliantly illustrates how quantum weirdness could, in theory, scale up to our macroscopic world. Showing that reality might remain undefined until it is measured, the strangeness doesn't stop there. Let's talk about something called quantum entanglement. It's a phenomenon so weird that Albert Einstein himself couldn't accept it, famously calling it spooky action at a distance. You can take two particles, it's like two electrons, and link them together in a special way so that they become entangled. This means their fates are now intertwined, no matter how far apart they are. If you separate these two entangled particles, sending one to the other side of the galaxy, they remain connected. If you measure a property of one particle, say its spin, you will instantly know the spin of the other particle. It's as if they are communicating faster than the speed of light, which according to Einstein should be impossible. Change one, and the other one instantaneously reacts, regardless of the distance between them. This has been experimentally verified time and time again. It's as if the universe doesn't see them as two separate things, but as a single, unified system, defying our common sense, notions of space, and separation. So what does all this mean for our understanding of reality? This is where physics starts to bleed into philosophy and even spirituality. The central mystery is the role of the observer. What is it about observation that forces reality to pick a state? Some physicists, like the legendary John Wheeler, have proposed radical ideas. One of them is the participatory universe theory, which suggests that the universe, in a sense, comes into existence through our observation of it. It suggests that consciousness itself might not be just a byproduct of a physical brain, but a fundamental aspect of the universe that plays a role in creating reality. In this view, reality isn't a fixed, pre-existing thing that we are just discovering. Instead, it's a dynamic, participatory process. We are not just passive spectators watching a movie. We are active participants in the creation of the cosmic drama. Does a tree falling in a forest with no one around make a sound? Quantum mechanics would ask. Does the forest even exist in a definite state if no one is there to observe it? These questions push the boundaries of science. They force us to confront the possibility that our perception of a solid, objective world out there is, at its core, an illusion. The material world may emerge from a deeper, more abstract level of reality governed by information, probability, and observation. Quantum physics doesn't just revolutionize technology, it powers our computers, lasers, and medical imaging. More profoundly, it revolutionizes our worldview. It challenges us to rethink the nature of existence, the boundary between mind and matter, and our own place in the cosmos. We've learned that the universe is far stranger, more mysterious, and more interconnected than we ever imagined. The solid ground beneath our feet might not be so solid after all. The journey into the quantum world is a journey into the heart of mystery itself, and we've only scratched the surface today. If you enjoyed this dive into the mind-opening wonders of science and want to explore more ideas that challenge your perception of reality, make sure you subscribe to David IB Course. Thanks for watching.